it's my pleasure to introduce Paroma Varma. Paroma is a fourth-year PhD student at Stanford, working on machine learning and in particular on weak supervision. In my opinion, weak supervision is like a really, really exciting approach to alleviating some of the issues around kind of how difficult it is to label training data. And in particular, she's worked on Snorkel, which is one of the most promising systems for doing that. And so I'm really excited to have her here to hear a lot more about the work that she's been doing at Stanford. So welcome.
Well, thank you for that amazing introduction. Hope I can live up to that and Snorkel can live up to that. So I'll do a brief overview of the work we've been doing around weak supervision and particularly our system Snorkel. Feel free to ask questions as I give the talk. If I don't get through all the slides, no big deal. So I'll start off. So Snorkel is a system to help program training data efficiently. This is work that I did during my PhD in Chris Ray's lab at Stanford, along with other members of the lab. So as we know, machine learning is everywhere. I'm kind of preaching to the choir here if I say that people are using it for, natural language processing, analyzing images, but also things that, ML wasn't thought to be used for, like things like networking or like data cleaning. And because machine learning has kind of exploded in its popularity, one of the things that we noticed was that people are spending a lot of their time kind of just working with their training data. And we call this shaping training data. And it's kind of this ad hoc procedure where people have to label their data. They have to make sure they have a good representation of the data they're looking for. They try different augmentation schemes. They try reweighting the data that they have and telling the model to focus on specific parts of it. And it's a really time-consuming process. And what we wanted to do was kind of focus on one aspect of it, which is the labeling part, and try to make it more efficient. So the key idea that we have behind our system, which is Snorkel, which is this cute octopus. Don't ask me why this has to do with labeling training data. It's like this long story about another project that was in our lab, but for now, octopus means labeling training data. The key idea behind this is essentially we want to take advantage of noisy sources of labels, which don't kind of work on an individual data point basis, but rather work on a higher level of abstraction and be able to model their noise and combine them so that we can get labels more efficiently. So before jumping into the details, I want to thank everyone in our lab who helped build this project, as well as our collaborators on the industry side who were really patient with us and tried out research code on their real data and gave us really helpful feedback. So to start off with Snorkel and kind of going through the basic steps of that system. Snorkel consists of three main steps. So the first step, which is the labeling part, is users write these heuristics that are called labeling functions. And labeling functions are essentially these rules that are not perfect, but they kind of encapsulate some knowledge people have about the data that they're trying to label. And I'll show some examples of that next. The second part of the Snorkel system is the actual algorithm that helps learn and model these heuristics that users have written. We need to know how accurate they are. We need to know if they're correlated in some manner. And once we have this information learned, we can combine them in an optimal manner to assign training labels to the data that we have. Once we have these training labels now, we can train any deep learning model that we're interested in. We just have to make a one-line change in terms of the loss it uses, but you can just kind of keep doing the rest of your machine learning pipeline as you were before. The first step, which I think the most important part of the system, but I only have one slide on it, I'll have more slides later on, is writing labeling functions. And we kind of see writing labeling functions as a way of encoding domain knowledge people have about the data that they want to label. So what this looks like for Snorkel, which is written in Python, are these little Python snippets of code. So in the first task that I have up here, we want to see if the chemical name and the disease name in a particular sentence have a relationship. Like, does the chemical cause the disease that's mentioned in the sentence? Now you can imagine going through every single sentence with different names of chemicals and diseases and labeling them one by one, like this is a true relation, this is not a true relation, and this can take a long time, especially if your data set is really large. What we do instead is we ask users to write these labeling functions. It can look for words in the sentence or certain patterns that tell us a good enough signal of whether the sentence is true or false. So in this case, we can look for words like due to or because and whether they appear in between the name of the chemical and the disease. Something else that we can do is we can also have negative rules. If there's clearly a phrase like not cause that appears in the sentence, then this relation is probably not true. We can do this not just for text, we can do it for images as well. Let's say we have an image and we used one of the out-of-the-box object detectors and we have bounding boxes for people and bikes. But now we want to know if we actually have pictures of people riding the bike in these images or not. So again, we can imagine crowdsourcing this entire task, training a specialized model for it. But instead, maybe we can make use of the bounding boxes that are within the image already and say something like, if the person is above the bike, it's probably true that the person is riding the bike. If the person is much smaller than the bike, then maybe the person is in the background and the bike is in the foreground. So that particular person is not riding the bike. The key thing to remember with these labeling functions is that we can write multiple of these, but none of them are going to be perfect. If you could have written a perfect labeling function, then we wouldn't need to do machine learning for our specific classification task. The second step now is given, yeah?
Have you wrote these rules, do they have to be mutually exclusive? Or?
No, that's a great question. They don't have to be mutually exclusive because we can actually learn their correlations as well. So, great, yeah? Yeah, so I can talk about a few example tasks that we had. We see for a binary classification task, for example, we see anything between 60% accurate and 90% accurate. Another key thing about these labeling functions is they can actually abstain. So what abstain means is that it'll return true if it finds a particular phrase, but if it doesn't find it, it's not going to return false. It's just going to return I don't know. So what you end up with is you have some labeling functions that are, they only assign a label to 10% of the data points, but they're 90% accurate on that subset, versus you have other ones that are only 60% accurate, but now they've labeled, say, 90% of the data points. So in order to learn their accuracies and model their correlations, we can't rely on any label data, right? Like the whole idea is to move away from hand labeling any data. So what we do instead is we just look at the overlaps and conflicts among the labels assigned by these different labeling functions, and we can actually use that to learn what the accuracy is. We do this in a factor graph-based model, and if we have time after the talk, I would love to get into details of that as well. And to answer your question, we do model the correlations among these labeling functions as well, because often we see, you have multiple people on a team writing these, and they're not exclusive. Both people have the same idea. They're trying to encode in these Python programs, and we don't want to kind of double count their vote. So we do need to know if they're related or dependent on each other in some way. Yeah.
When you're comparing their accuracy, are you comparing, this is not comparing to a ground truth, right?
No, this is not comparing to ground truth.
Them, but then what do you say when you say that this is 90% accurate? That's not really, how do you say that it is actually 90% accurate?
Right. So when we learn the accuracies, we're learning how accurate it is compared to ground truth. So the reason we can do this is we have, at a high level, the intuition is that if two labeling functions tend to agree a lot, they're probably both fairly accurate. And then you have a third labeling function that randomly agrees and disagrees with these two, then it's probably not as accurate. Mathematically, we can form this covariance matrix that helps, where we basically solve for this variable of how correlated are the labels that the labeling function assigns to the ground truth variable. And I have that towards the end of my talk to go into the details of that. Yeah, that's the really cool and interesting part anyways. Yeah. So once we've kind of modeled the accuracies and we've learned the correlations, what's the next step? So the next step that we want to do is we actually want to use these labels that we've assigned to the data and train a machine learning model with it. One of the questions that we commonly get is, you have all these heuristics, say you have 10 or 15 heuristics, you've learned their accuracies, hopefully really well, you've modeled them, you've combined them according to that, why not just stop here? Why can't you just use these labels as kind of your end product? And the reason is because these labels that's been assigned to the data, it's not using all the information available in the data. Let's go back to the text example that we had. It's only looking for certain phrases, like it's looking for the phrase due to, or it's looking for the phrase not cause, but it's ignoring all the other information that's present in the sentence that, say, an LSTM could pick up. So once we have these noisy labels, we do want to take advantage of all the rich structural data that we have access to, and then train another N model using these labels. The second reason we want to train another model is, remember, these labeling functions don't necessarily assign a label to every single data point. So they might only end up covering, say, 60 or 80% of your data points. But a model that you build, you want it to be able to predict a label for any data point that it sees. So that's another reason to kind of take these labels that you have, treat them as training labels, and then train another N model with it. So one of the things we did after we built the system, yeah?
Won't the model then encode the logic in the labels, or will it be able to do something more than what the labels have?
Yeah, that's a really good question. So the question was, will the model just encode the logic that was in the training labels that we got from the labeling functions, or will it be able to generalize to other information? So we've seen in practice, if we have access to a large amount of features, which is usually true for deep learning models, it's able to generalize beyond just the logic that's contained in these training labels. Another point is that when we assign training labels, they're not just, it's not, say in a binary task, it's not just true, false, true, false. We actually have an associated confidence with the labels that we assign. So we have labels like this is 40% likelihood of being true, this has 60% likelihood of being true. So encoding that kind of confidence parameter in the training labels also helps the N model go beyond the logic that was encoded in the labeling functions.
When you say encoder, that's not part of the label function, right? That's something you do after the label function.
So the encoding part of...
The label function is not going to say, I'm 40% sure this is...
Right. The labeling function is just going to say, this is true, this is not true, I don't know. When we run our model and learn its accuracies, we essentially do sort of like a weighted majority vote across all the labels that were assigned, and we get confidence according to that. We're trying to do something right now in lab where the labeling functions can also encode a confidence, because sometimes you have, say, another model that you might be using as a labeling function, and then we should be able to learn that accuracy as well. And we hope that will do much better than just having labeling functions that are binary. What we did once we had kind of the Snorkel system built out was we wanted to see if it's actually easy to use. Obviously, for people in lab who were spending time building it, we knew exactly how to write the labeling functions for the tasks we were looking at. So what we did was we held this workshop where we had biomedical scientists come who had very beginner knowledge of Python, and they had their own tasks that they wanted to work on. And we had them hand label data for 7 hours one day. I don't know why they did it. They were very kind. We gave them food. And then the second day, the next 7 hours, we spent teaching them how to use Snorkel, how to write labeling functions for their task. And then they spent some time kind of writing their labeling functions, iterating them, editing them, collaborating on them. And what we found was that given the same amount of time, writing labeling functions and training an N model does almost 25 points better in terms of model performance than hand labeling data. And the main reason for this is the scale that we can label data at. You can write 5 labeling functions and apply it to 100,000 data points, but you can spend hours and hours having to manually hand label those data points. So even though the training labels that you get out of this system are fairly noisy, it's the scale that makes it work so well at the end. Yeah.
Oh, so you said 25% better, like in what metric?
Oh yeah, so this was an F1 score of the N model.
Is that dotted line the baseline?
The dotted line is the baseline, yeah.
Is that like a random baseline or a rule-based?
So that baseline was we labeled a small amount of data that, when people are writing their labeling functions, they kind of want to know, is this like logical or not? So they labeled around, I think, 100 data points or 50 data points. And then they were just testing their labeling functions with it. So that baseline sort of represents, if we only had that very, very small amount of label data, how would we do?
And then do you have a baseline of how the rules themselves perform?
Yeah, I don't have it here, but I think I might have it in one of my extra slides that I can show towards the end. But in general, for text examples, we usually have 15, 16 rules. If we just learn their accuracies, combine them, assign probabilistic labels, we see that the F1 score is around 30 something. And then because we train an LSTM model at the end, we're able to generalize and get that 48 F1 score that we have up here. So another thing that we did once we kind of went through this process of writing labeling functions in Python is we wanted to make it kind of more widely applicable. Not everyone might know how to write Python. They might not know how to iterate in that context. So we wanted to make this process of writing labeling functions and encoding domain knowledge much easier. So we made this beautiful pyramid, which we were trying to say, like people had machine language before, which is kind of like manually labeling data. It's kind of painful to go through individual data points and label them by hand. But now, they kind of went up the stack, and now we have declarative interfaces, we have applications. So we kind of wanted to do the same with this idea of being able to label data. So instead of manually labeling them, we now have a way of like programmatically labeling them. Maybe we can do something like label them using natural language, or at the end, do some sort of semi-supervised structure to be able to create them automatically. So I think this is one of my favorite projects in lab, which is using natural language to label data automatically. So 2 reasons this is my favorite. One, we used this project and we collected explanations from Amazon Mechanical Turk. And it was a really easy comparison because that's kind of what people tend to do when they want to collect training data. And our thought process was whenever people are labeling data on a platform like this, they have some reason in their head for why they're assigning a label of, say, true versus false. And if we could only capture that reasoning in their head in some form, we could have so much extra information that can help us label data much faster and more efficiently. So what we did this time, instead of just asking people to hand label data, we also asked them to tell us a reason why they assigned a particular label. Say, going back to this chemical and disease relation task, when they said, okay, this is true, they said, the reason I think this is true is because I saw the word because in the sentence. Or the reason I think this is true is because the word due to was in the sentence. And there were a collection of these reasons that we collected. What we saw was that with just 30 of these explanations, we were able to label training data that was so good that it matched the performance of a machine learning model trained on 600 hand-labeled examples. That's not saying much because saying, oh, we have 600 hand-labeled examples doesn't sound that great, but it's just about the scale. We were able to kind of reduce it by a 5x factor. In terms of time, we were able to reduce it by around a 2.5x factor, and that's because it does take a little longer to type out the reasoning that you have than just to label individual data points one by one. Another thing that we were excited about was kind of moving away from the text case to cases where you have numerical data or where you're writing these heuristics that are threshold based. And that what we saw was that it kind of required a lot of guess and check work. And it could become painful. Say we had this example of, is the person riding a bike or not? We could say, is the person above the bike? We can say, is the person bounding blocks 2 pixels above the bike, 4 pixels above the bike? And then now you've made the process of writing labeling functions almost as cumbersome as kind of individually labeling those data points. So what we did was we sort of tried taking a semi-supervised learning approach where we use a small amount of labeled data, so say a 50 labeled data points or 100 labeled data points, and a large amount of unlabeled data, around 100,000. And we were able to kind of automatically learn these labeling function templates with certain thresholds pre-filled. We gave it to the user and they could sometimes adjust it based on their domain knowledge. Sometimes they just kind of took it out of the box and fed it into the Snorkel system to see how it does. And what we saw was that for numerical-based processes, this system worked really well. It usually beat the hand-tuned rules by almost 10 F1 points. Where it didn't do well is for text, because in text, when people write labeling functions, they kind of write regex rules. They look for common phrases. They know, maybe the word like at needs to be at the beginning and because of needs to be at the end. But we weren't able to generate templates that were so complex. So that's kind of still something that we're working on. And hopefully, while we're like trying to build templates for text, people can just use the natural language interface instead to label the data. So I'm at the end of my talk. So the three things we kind of believe in kind of moving forward with the research is that we kind of see supervision as an interface to be able to label data, and we want to move to higher and higher levels of supervision so that labeling training data becomes much easier and much more efficient. We believe that our technology of being able to model the noise and the correlation in these different sources of labels is what really helps us scale and get the numbers that we're getting. Other things that are going on in lab are related to kind of making machine learning easier. So we look at efficient model training, low memory training, different sorts of embeddings that are more stable and accurate. So if you have questions about that, I can talk a little bit about those as well. I just won't know that much about it. Thank you. Yeah.
Can you speak more about modeling of the noise?
Sorry?
The second bullet, modeling noise.
Yeah, so modeling noise, actually I'll show the slide I was talking about, which kind of goes through the math of how we actually learn these accuracies. So when we're modeling noise, all we mean is we are able to kind of capture how accurate these labeling functions are and how correlated these labeling functions are. So let's just start with accuracy, right? So what we do is we build a covariance matrix that's shown over here. And what we see is that O is these labeling functions that we have, and S is sort of the ground truth Y label. So if we can kind of learn this parameter, which is the covariance between the labeling functions and the ground truth parameter, we're fine. That's just going to give us the accuracy out. The problem is we don't have the ground truth, so we can't really completely see this variable that we want to solve for. So what we do instead is we rely on one little neat trick that says the inverse covariance matrix of any kind of factor graph that's graph structured is also going to be graph structured. And what that means is that in our factor graph model, we have our ground truth variable over here, and we have the labeling functions all correlated in some manner to this ground truth variable. So if we take our inverse matrix, if we take our covariance matrix and invert it, the entries where there are dependencies, we're going to have non-zero values. But we still have a problem. We have to invert this entire matrix to be able to see that structure. And again, we don't have access to that entire matrix because we don't have access to the ground truth variable. So what we do instead is we look at this matrix, which is supposed to be graph structured, which means this top left corner of it is also graph structured. Then we use some matrix inversion identities to be able to represent this variable in terms of the other variables that are in this matrix over here. I'll break it down to this simplistic part. So this is the sparse matrix. This tells you what correlations we have. We learned this using a robust PCA approach. Sometimes it's user-defined, so this is known. This is something that we can observe. This sigma O over here is just the covariance of the labeling functions themselves. So we take the labeling functions, do a cross product, and we get a matrix that's just the agreements and disagreements of the labeling functions. And then this is this low rank matrix that depends exactly on this variable that we're trying to get out, which encodes the accuracies of these labeling functions. So once we solve this problem using a matrix completion approach, we can solve for Z. And then because we know exactly what the formulation of Z is compared to this constant C and the sigma O observable matrix, we can solve for the accuracy parameter. So we used to kind of solve for this in a Gibbs sampling way, kind of have the factor graph sample multiple times to learn the parameters. It was really slow, and when we started to move towards applications with 100,000 data points, it used to take 10-15 minutes to run, which was crazy. So this new approach where we're just doing a matrix completion thing, which we've implemented in PyTorch and TensorFlow, that's much faster. With 100,000 data points, I think it takes a second, if not less. So this matrix completion approach kind of lets us do a lot more, a lot faster. And now we've also looked at how we can do multitask supervision, how we can do supervision across video and other temporally related data types as well.
So the ZZ transpose is a way to pretty much estimate the covariance of the observed versus the labeling
Exactly. ZZ transpose captures the accuracies of the labeling functions. Yeah.
Where does the graph structure come from? Isn't every labeling function potentially correlated with every other?
Yeah, so the graph structure, which is shown here, it sort of comes from, first, the labeling functions all have to be correlated in some manner to the ground truth label that we have, so that's why. And that's the variable that we can't observe. So that's essentially a latent variable in our factor graph. The second thing, in terms of all the labeling functions being correlated in some way, we're okay as long as they're not correlated with each other, kind of conditioned on the ground truth variable. So obviously, they won't all be independent completely, because if they were all independent, they're going to end up being random and have no signal about the data. So as long as conditioned on the ground truth variable, they're independent, or we can learn how the dependencies occur, we can still learn their accuracies. In the theoretical component of our paper, what we show is we need to have at least 3 kind of conditionally independent labeling functions. The rest of them can be correlated in whatever manner, and we can still learn their accuracies.
Okay, so you don't know the sparsity structure in minutes.
So there's 2 ways of going about this. One is we know the sparsity structure in advance because, maybe when people wrote their labeling functions, they said, oh, one looks for the word cause, one looks for the word not cause, they're definitely correlated. Just recently at ICML, we had a paper on how we can learn this sparsity structure. And in this case, what happens is the only thing that's known is this variable over here. And now we do this decomposition of a matrix into a sparse component and a low rank component. And in terms of implementation, we essentially use CVXPy, and we have some constraints on the structure of the sparse matrix as well as the low rank matrix, and then we can solve for both simultaneously.
Do you have a GitHub for this?
Yeah, so all the information is at snorkel.stanford.edu. That has a link to the GitHub page for the project, as well as all the papers and some blogs related to kind of the theoretical work that's gone on in the lab as well. Yeah.
Can I ask? Okay, I'm going to ask a question from a perspective of someone who actually didn't really understand most of the math you just.
That's totally fine. That was me like 3 years ago when I joined lab.
From what I understand you're saying, it sounds as though there's like some wizardry happening here, where you put in what feels like a small amount of information, and then you get out something that seems like a lot of information. So I'm wondering how does that intuitively make sense, right? If the labeling functions don't capture all of the information you need to actually make the decision, because there's other things about
the data, right?
About the data, right? That are too complicated to write as a labeling function. Like, is that information come from somewhere?
Right.
Does it just cause an upper limit on the score you can get? Like your scores are like around 25, 50. Like, so that seems not too surprising. Does that mean that it'd be really hard to get up to 80 or 90 because the information isn't in the labeling?
Yeah. So I think the score, that was just for like a particular task. So I'll just kind of throw up this model. What we saw was that by doing this weak supervision approach of kind of using labeling functions to assign labels to training data, we actually got within like 1 point if we had actually used all the ground truth labels available to us to train the same model. So I think the scoring was like more specific to the data set that we were looking at. We have seen scores up to like 95 F1, 98 F1 for certain applications as well. The first question that you had, which was about kind of like how does this wizardry work? I think that is a really good question, and it has kind of 3 components to it. So one, we write multiple labeling functions which do capture kind of multiple aspects of the data. So there is a lot of information that we are capturing by combining the information from these different labeling functions. The second part is that we can model the noise in them. So we know exactly when to trust one labeling function over the other. And I think that gives us a little bit of an edge versus just trusting all these signals blindly and equally. The third thing is we only use this approach to assign training labels. The question that you asked about, it's ignoring a lot of the information present in the data that we kind of leave to like these complex deep learning models you have. So with our labeling functions, we only generate enough training data, which is definitely noisy and not very accurate. But then we allow this deep learning model to kind of use that noisy labeled information that we have and kind of generalize using the access it has to like these deep learning features and the sentence structure and things like that. And then it's actually able to get that big bump to be able to match, what we would get with ground truth labels. So yeah, just using the labeling functions usually doesn't do that great. Like that's why you can't use it as a final predictor. You have to end up kind of training another model with it at the end. Yeah, but I really like that question.
Question. So, it sounds a little bit like a learning problem on the labeling itself. So the labeling function is kind of like a weak predictors, and you're boosting to come up with this. So in that sense, then it depends a lot on your labeling functions, and also if your data is balanced, or if the labels are balanced or imbalanced. So does this approach, have you tried it on very heavily imbalanced?
Yeah, so that's a really good point, and that's something that we recently worked on. So in the mathematical formulation that I just showed, we have another more complex one that I don't have on my slides, where we kind of learn a different accuracy and correlation parameter conditioned on the true variable. So then if you have class imbalanced data sets, we can actually handle learning and accuracy depending on if it's like the majority class or the minority class. One of the most imbalanced data sets that we've worked on it's currently in a Nature paper where we had only 1% positives and 99% negatives. So we were able to apply 6 labeling functions in that case, and we got really good scores. I think that's another one where we got 80 or 90 F1 score, versus like before, given the amount of label data that they had, they were getting 20.
You mentioned that you have confidence for each labeling function and accuracy for the overall labeling logic. When you usually use a supervised learning model, you have like labels.
Right.
Either this label or that label or that
Yeah.
label. How do you encode this confidence in the model itself?
So in a binary case, instead of just passing in a hard label of 1, -1, we instead pass in an array. So it gives you the confidence that it belongs to class 1 and a confidence that it belongs to class 2. So we do have to change the input layer a little bit so that it can accept an array. And then in terms of the loss, we usually use BCE with logits or a cross entropy loss, which can accept probabilistic labels. Exactly. One more question.
Yeah, so I was just, correct me if I'm wrong, but I want to like understand this process, like coming from somebody who don't necessarily have enough training data to use Snorkel to complete their project. So, so it sounds like what you need is you would still need labelers to label some of the data, and they provide, in one of your high level, we're extracting kind of rule-based labeling function from their sentences.
Right.
And then from there, we build a rule-based a model that's encoding the labeling function. And then from there, it generates kind of data from the model.
Right.
And that's how you get labels, and then you can then pipe into the actual training.
Right. So I think with the example that I showed, where you have a natural language explanation that someone actually writes, and we convert it to labeling functions, so that you don't necessarily have to go down that route. You can just start writing labeling functions from scratch, in which case you don't have to collect any kind of label data from the beginning. You do need to have access to unlabeled data though, because say if you don't have, you write your labeling functions, you have to apply it to some set of data points, which you then will use to train your end model. So sometimes we've seen applications where, there's only maybe 100 unlabeled data points. So there's not even enough unlabeled data. We have another project that's on that snorkel.stanford.edu page, which uses kind of a very similar labeling function based approach to augment the data set. So then you can kind of combine these two approaches if you don't have enough data to first augment your data set and then kind of assign noisy labels to it to then do the training process.
Your labeling functions, some of them have, things like if person and size and minute. So I would imagine that coming up with the notion of person would be compute intensive itself. How does that is handled in function execution?
Yeah, that's a really good question. So the question is, if you have something like, is there's a person in the picture, then do this. But whether the person is in the picture or not is also going to be noisy because it's coming from another deep learning model. So in our image-based algorithm that does weak supervision, we actually learn not only the accuracy of the labeling functions, we also learn how accurate these inputs that the labeling function takes, we call them primitives, how accurate they are. So we have some notion of accuracy on two scales. One, like how accurate is your object detector, and because of that, how accurate is your labeling function going to be. So we can model noise at both those levels. Yeah.
What's going on with the bold humor data set?
Yes. It was the, put this in the paper and then everyone's going to notice it. So what's happening here is all these lines are essentially using weak supervision, and we were able to label twice as much data using weak supervision as we had ground truth labels for. So we're just saying that if you have labeling functions, you can label twice as much data noisily, but even that helps improve your end model score.
Would you trust labeling functions for medical applications?
Yeah, so that was a big question when we were getting reviews for this Nature paper I was talking about with the class imbalance, because it was to assign labels to these really rare heart malformations in children. So it's a big question of whether we would trust the labeling functions or not. I think compared to just general deep learning, when there are a lot of questions about interpretability and trust, in this case, there's actually some way of mapping back to where you got the label from. Because when you look at a label assigned by a labeling function, you know exactly why it got assigned that label, because it says, oh, it's 50% because of this rule, 80% because of this rule, and 30% because of this rule. So you can map back your errors to exactly where it's coming from. Another thing, we never use these labels directly to assign predictions. We always train like an end machine learning model with it. But if there's some sense of kind of auditability that we want, we can look back at the labeling functions. But I think it still has the same issues that kind of deep learning is facing today of how interpretable is it and how much should I trust it.
Some follow-up question about the labeling function. So using the Snorkel, then general strategy, which one would be more beneficial, to have a lot of very simple label learners, like almost like a linear kind of thing, versus a few but very complex and more layered labeling functions?
That's a good question. So do we want to have a bunch of really simple rules, or do we want to have a few very complex rules? Theoretically, my answer is just put them all in, because it can model the accuracies of all of them, so it'll know exactly when to trust one versus the other. In practice, you do kind of have to see, you have to play around with it a little bit. I haven't seen a big difference between using a few complex ones. Like for images, we usually just use 4 or 5, and then many simple ones, because in text we use up to 20 or 30. So we've seen kind of both extremes, and it's very application dependent on which set of labeling functions would work better for you. Theoretically, all of them. Yeah.
So, building upon that, if there are some bad labeling functions in there,
right?
Would it be better just to get rid of them rather than putting them all in, or?
So what we've seen is that usually if people write a labeling function and they have it in there, it's good for something. Like it might be good for a small subset of the data, but it's going to have some signal in it. So we usually tell people not to throw away anything that they've written unless it's, labeling the same thing as another one. But if it has any useful information, we are usually able to model that, okay, like this is overall, it's only like 50% or 51% accurate. But on this specific subset of the data, it's actually 80% accurate. So only trust it when it belongs to this specific subset of the data. So that's like another layer of learning we can do. So usually we tell people don't throw them away if we are able to kind of model these fine-grained accuracies. If we can't, then you can always just like remove a row from this matrix you have, run the model again, and you're like, oh, it's doing better. So I'll remove it. I'll come back to you. One more question here.
So what's the process of iterating the development of your labeling functions like? Like if you run it once with some functions, you get some result, does that tell you something about how you might want to change labeling functions and try again?
Yeah, so we do have some really simple tools built into the code base right now, which tell you what the overlaps and conflicts between the different labeling functions are. So that can help sometimes. If you see you have one labeling function that never disagrees with anything else, that's not adding too much to it. Like, you want to model it in a way that it actually disagrees with some of them. In terms of iterating, the model takes a few seconds to run, so it's not a slow process. You don't have to wait or like watch any gradients go up and down. But we've seen that depending on the application, it can take somewhere from 1 hour, which was this case, because we had images, to a few days for some of the text applications.
But then after that result happens,
Yeah.
I mean, is there a way to go back and say, okay, now I want to improve my labeling functions to get a better result?
Yeah, you can definitely do that.
How would you know what to do?
So sometimes what we see is people, they generate their training labels, they train their end model, and then they see that their end model is kind of always making mistakes in a particular subset of the data. So then they can go back to their labeling functions and say, okay, let me write one that's very specific to this subset.
So just a comment, I'm just wondering, how is it different than the traditional 1.0 model of writing an algorithm as you go more and more accurate labeling, you're essentially writing an algorithm to predict.
Yeah.
Second thing is the final validation and test set hand labeled with the ground truth, or is that also?
So I'll answer the second question first. The test set is hand labeled, so that we would need no matter what we do with machine learning. So whatever people have for their specific application, we use that test set, and it's definitely labeled by hand. The first question, which was about, the more you iterate on your labeling functions, the more you're building out an entire algorithm. That's why we try and keep these sessions of writing the labeling functions kind of to maximum a few days. So that'll be like total of like 6 hours of one person writing them and iterating on them. And they usually don't touch it again unless their data distribution changes. Sometimes we do get away with, just sitting together and writing for an hour. Because if you kind of try to over-engineer your labeling functions, and they become super accurate, then maybe you've solved your problem already, right? The idea here is that you can't over-engineer them because you just don't have access to that data, and it's just not a very logical problem that you can do this with.
Yes. So on the example on text, you showed how you can just use regex, and people can say what they're looking for, and you can search in that. But maybe that same thing doesn't work with images, right? It's not that easy to search in images.
Yeah.
And if you have open source model to object detect, that's great. But what you're doing is not an open source model. What are some more challenges you faced with image-based labeling and using Snorkel?
Yeah, I think image-based labeling has been one of the tricky things. That was my first project when I joined lab, was actually extending it to image-based work. When we had, these object detectors, it's really easy because you have bounding boxes you can write labeling functions over. For medical applications, it's a little more challenging because you don't know what to write labeling functions over. You can't write it over raw pixel values. Like, that just doesn't work. So you still need to depend on some other existing algorithm for that specific data set that you can use. Say, like something that does coarse segmentation. Maybe something even that's not a deep learning based model, but just from like scikit-learn. It just does like a threshold-based operator. And then, once we have something to work with, say a binary mask, then we can write labeling functions over that information. And those masks themselves are also noisy. So I think we had this question before about how do we model that noise as well. So for image cases, we add another layer to our factor graph because we need to model that noise as well. But images in general are harder to write labeling functions for as well because there's not a lot of signal you can kind of call upon. You always have to stick to, I'll use the area, I'll use the perimeter, I'll use the intensity, I'll use maybe like the ratio of area and perimeter, but that's it. Like after a point, you can't extract as much signal as possible.
We have time for one last question if anyone has one. We have to unfortunately move on.
I know you said you didn't go too much into it, but I was curious what you're doing with converting the embeddings and making those like more robust.
Yeah, so in our lab, we have two pieces of work. One is around using hyperbolic embeddings to look at data that has some sort of tree structure. So right now we're using it to create parsed trees because we think hyperbolic embeddings are going to work better than embeddings that are created in the Euclidean space. Another project that we have with embeddings is building a system around them because a lot of times for text data, we see you have to kind of retrain your embeddings and recreate them. And there's a lot of issues around stability. So we are studying how stable we can make these embeddings and how we can make the process of retraining more efficient, given we have new data coming in.
Are all those challenges coming in the medical space for you guys?
In the medical space, we haven't seen it as much. I think we've seen it mostly for some biomedical applications. So they kind of look at all the abstracts from like 1 year and they want to build embeddings around that for a particular applications. And the next year rolls around and now you have another set of abstracts that you have to kind of incorporate in the embeddings that you created. So those are the kind of challenges that we're looking at. In the medical space, I think we've been focusing on the weak supervision aspect of it and labeling images. Yeah.
Great, let's thank Paroma again.